Hey everyone, how's it going? This is Siri and I'm back with another PyTorch video for you guys. And we're going to be continuing our discussion on tabular data and how we represent them of like different categories. And we're going to be continuing our example that we've started with the wine quality CSV file. Okay, so let's retrace our steps. Okay, first we're working with tabular data, which is just like, a data table. Pandas is great for that. I would like any sane person would use that, but we're not actually. So we're instead using the CSV module and NumPy. And so first we're importing both of them, right? We have a path. We converted it to a NumPy ND array. We created a variable that held all the column names. Okay, and we printed out the shape and the data type. Okay, this is the column list, fixed acidity, etc. So now from a NumPy array to a PyTorch tensor. Okay, then we talked about the three types of data. Okay, and it's basically what's the sort of relationships between the values in the array. And so there are three ways to characterize that. We can have either continuous variables, ordinal variables, continuous values, ordinal values, or categorical values. Continuous values, incontinuous values, order matters. The difference between them matters. If you have units and if you're counting, it's probably continuous. An example is the house price regression problem. We have too many S's here. Okay, and in ordinal values, order matters, but the difference between them does not. For example, small, medium, large. Categorical values, the order does not matter, the difference does not matter. And this is basically, an example of that would be probably assigning numbers or arrays to different categorical values, like the city to the city name, the state name, the country, whether people like skiing or not, like yes or no. Okay, so it's categorical, whether the sky is red, whether the sky is blue, red, blue, right? These are all categorical values, and it doesn't matter whether you give Boston 04 or whether you give New York 06, it doesn't matter. Right, so that's, the order doesn't matter, first of all, and the difference between the numbers does not matter at all, because they're not representing real values, right? Okay. Real numerical values. Alright. So that's that. If you need to go through this again, and if this wasn't enough, feel free to check out the previous videos we made, and we went through. Okay? You'll get a better idea of what tabular data is and what we can do with it. I discussed it in more detail. Okay, but in this video, okay, by the way, the types of data here tell you, okay, so for example, if you have this one, or this one, or this one, the type of data you have tells you whether or not you need one hot encoding. What's one hot encoding, you ask? Well, we're going to be discussing it here. Okay, so one hot encoding is great for categorical values. Okay, and it might be great for ordinal values as well, but let's start with categorical because it makes more sense. Okay, let's say you have blue marbles, red marbles, and green marbles. and purple marbles. Purple marbles. Okay? And you can't just pass in to your neural network, hey, this is blue, this is green, this is purple. It's not going to understand. Okay, the mathematical model does not recognize real colors unless it's in a mathematical form in which it can understand. So how do we represent these values, or these categorical values, as numbers? So what one-hot encoding does, one-hot encoding is a way to represent these categorical values. Okay, so one second. Let's make this markdown. Okay, so one hot encoding is a way to, like, literally encode, right? It represents, okay, it's a way to represent categorical values. Okay, and how do we do that? Okay, so you see how we have 1, 2, 3, 4 different classes, right? Okay, so each color will be associated with a different vector. And a vector is just, just a collection of values, right? It's just going to be a 1D tensor. Because a 2D tensor would be a matrix, right? So, okay, and your vector, okay, this is just a way to write it. You could use like parentheses or whatever, right? Okay, so they will have the same number of values as what? As the number of classes. So each color is associated with a vector of size x, where x is the number of classes. All right? So, well, I just copy pasted all zeros. How do we tell them apart? Well, at one index value, that 0 is going to change to a 1. Okay? You can make this a 1. If I make this a 1, it wouldn't work out. Okay, let's make the second index value a 1. Here, let's make the third one. This is actually the second index value because it starts at 0, 0, 1, 2, like that. Okay? Okay, and then now the last one. Okay, so now, if you say, hey, what is this associated with? 0, 0, 1, 0. That's associated with green. And the model will do some sort of math with it, and it'll output, hey, this is the value that I'm getting as our like prediction, and you get 0, 0, 1, 0, because that's what all it knows. At the end, you would probably have to convert that back to green. Remember, it's a two-step process. First, you convert the categorical values to your vectors, and then once you're done with all that, and once you're all good, you trained your model, and we're nice and happy, we turn it back into the colors that we can understand. Let's go back and look at something important. Now that we've talked about what one-hot encoding is, it's actually a pretty simple concept, right? Like we're just assigning vectors to the different categorical values. But when we go back to this definition here, categorical values, it's not really a definition. It's rather like a set of rules that it happens to abide by. Right? The order doesn't matter. Does it? Okay, and the difference does not matter. Okay, it's probably best if we put the example on another bullet point, right? Okay. So order does not matter. And difference does not matter. So what are we saying here? Does it matter if blue is 1 0 0 0? Or could blue also be 0 0 1 0? Can blue and green swap values? Can I say green is instead 1 0 0 0 and blue is 0 0 1 0? Yes, I can. It doesn't make a difference, right? There's nothing like about this vector that signals, hey, this is green, unless you specifically define it to be so. Okay, so that doesn't matter. The order, like, it doesn't matter at all, right? There is no order. It's not numbers, right? They're not numbers, right? So, yeah. The only thing that matters is that they're all different because these are all different colors. Okay, I think you get the point now, hopefully. But some of you might have the question, why do we need vectors? Why can't we just say, oh, this is 1, this is 2, this is 3, this is 4? Why can't we just assign different ones different numbers? Well, if the difference between one hot encoding and what you would call, what I just said was like integer encoding, is that if you use real numbers, like if you say this is 1, 1 second. Let's copy this. If you say this is instead 1, this is 2, this is 3, this is 4. This would be integer encoding. The problem with this is that your model is going to think that there's a real relationship between each of these, that there's a specific relationship. You see, the difference between 1 and 3 is the same as the difference between 2 and 4, right? Your model is going to think, oh, that must mean something. I must catch a pattern here, right? Blue is related to green in a way that blue is not related to red. There's a specific relationship between the different colors. No. Each of them is like completely random. There is no relationship between, or at least there is a relationship. What I'm trying to say is that the relationship between each of the colors is the same. Blue and red's relationship is not any different than blue and green's relationship. Or you could pick any other colors if you wanted to. But it might be, like, it might work for some circumstances. I'm not saying that you should completely avoid it, right? There are some circumstances where integer encoding works, where the difference between each of the values is, like, it matters, and this is a nice way to represent that. But for these colors, or maybe for animals, maybe if we had giraffes or zebras, or like elephants, right? Those are categorical values, and the order and difference does not matter. So you would use, okay, by the way, so you would use one hot encoding. Actually, it's probably not a great idea to use one hot encoding for ordinal values. I take that back. Another place where you could use one hot encoding is when you have like fractional values. To use one hot encoding. If you have fractional values and if your output doesn't make sense to be a fractional value, and if you need it to be like and you need it to be an integer, then one hot encoding is the best, because integer and encoding, there's no like limitation to what your model can output. There's no specific thing saying, hey, like blue is 1, red is 2, green is 3, purple is 4. Yeah, that's right. But the computations that go on inside could completely change, like, you know, what you output. And there's no guarantee that the output that you get is going to be the same sort of value that your input was, which was an integer. There's no guarantee that your output's going to be an integer if you used integer encoding. So that would be a great place to use one hot encoding. So where fractional values aren't, you know, reasonable. Okay. Great. Okay, let's get back to our original example that we were working on with the wine quality. Okay, let's go through the implementation. Now you know what one hot encoding is, and you know, hopefully you get it, right? You're just finding a way to represent this data, and it's a sort of data that's very, it works very nicely with tensors, because these are vectors, like I said, and like you can see here. Okay, so yeah, 1 second. All right. Okay, so first of all, let's print. What do we have here? Before we print anything out, let's define what we want to print out. I want to print out the target values. Yeah, let's do that. So let's say target is equal to wine Q, all the rows, last column. Okay. Let's convert it to a long. And when we print it, wine quality is not defined. Okay, we probably need to rerun everything. All right. Okay, so we get some values. Okay, 10. Okay, just wanted to show you guys some variety. Okay, so now you see some different numbers. Okay, well, it's just, okay, good. So this is setting this up for one hot encoding. This isn't it. Okay, we have some more stuff to do. Okay, in order to implement one hot encoding, we need to use scatter. Okay, the underscore tells you that we're modifying the tensor that we're currently looking at. We're actually modifying it. We're not just creating a copy and then modifying it and returning that. We're actually modifying the thing we're holding. Okay, And okay, so that's what scatter does. And it takes in a tensor, okay, obviously. And it's the tensor of targets and then a number of indices. Okay, and we'll see how that works. So first let's print target.shape. Okay. Good. So these are just the targets. These are the answers, basically. Okay, and they're the same number of rows. These are how many samples we have targets for. It's basically every sample. And then let's print target.unsqueeze. Let's pass in 0. Let's print that .shape. Okay, so what unsqueeze does is that it adds a dimension of 1 at the specified index, and now we're just getting the shape. Oh, I said okay, forgot the U. Okay, wrong spot. Okay, so we added a 1 at the 0th index. And you'll see why in a moment. Okay, target.unsqueeze. Now add it at 1. Now to .shape. See? Okay, so target 1 hot. Okay, so now we're actually going into the 1 hot encoding stuff. So this is probably where we're going to be using scatter. So first torch.zeros. Okay, see, because all of them were zeros. We first need to initialize something full of zeros, right? That's what we did originally. I first created a whole vector of zeros, and I copy pasted it for red, green, and purple. That's what we're doing here, basically. We're initializing them with all zeros, and then we're going to be changing up the values. All right, so let's say target dot shape of 0, right? Because there are these many zeros. We want as many zeros as there are classes. So that's why. And 10. All right. So these are the number of samples, like I said. And yeah, so okay, so if we take a look, I'm assuming okay, whatever. Yeah, so let's do target 1 hot dot scatter. So here and in place, remember. So we don't need to set it equal to a variable because we're modifying the real target 1 hot. Okay, and the first dimension is going to be the dimension along which the following 2 arguments are going to be specified. So we're going to have 2 more arguments. The next one is the column tensor indicating the indices of the elements to scatter. So, which indices should I put non-zero values? Let me know. Alright, so we are going to do target.unsqueeze again along 1. Okay. And then we're gonna you can put in any non-zero value here. It doesn't need to be 1. You can put 8, you can put 9, you can put whatever, as long as they're consistent. But the convention is to just use 1. So let's do 1.0. Okay, so what value should we scatter? Where are the indices we should scatter it along? And what dimension are we looking at? So when we run this, okay, we basically get zeros. No, we basically get, values of arrays of 0, except for one spot, like we discussed up here. Okay, so let's check this out. If 1.0 in target 1 hot, which we are definitely expecting, right? Because we scattered it. We scattered the ones along the, on this array, right? On target 1 hot. So we're definitely expecting to see 1. Okay, so let's just print. Yes, it's true. Okay. Yes, it's true. All right. This, by the way, the second argument of scatter, which we have here, target.unsqueeze1, is supposed to have the same number of dimensions as the tensor we scatter it into. Obviously, right? Because you're telling me to scatter along these dimensions, but you don't specify all the indices that you want me to do it along. You have 4 colors, but you only specify 2. Right, so that's what an important note to keep in mind is, since target 1 hot has 2, it has 2 dimensions. One is the 4,898 and the other one is the 10. We need to add an extra dummy dimension to target using unsqueeze. So you probably know how unsqueeze works by now. So we have target unsqueezed, because if you take a look at target 1 hot dot shape, see what we expected, right? So let's do target unsqueezed is equal to target unsqueeze 1 squeeze. Okay, we add an extra dimension. Okay, so now each one's in its own individual array. Alright, so maybe the last thing we should do in this video is, normalize it to the best of our ability at this point. Let's just calculate the mean. So let's say data mean. Mean is just the average, by the way. Okay, what data are we looking at? And dimension is equal to 0. Yeah, we didn't define data. So data is basically everything that doesn't include target. So where did we define target? Here, right? Let's define data in the same spot. Data is equal to 1q. Also every row and every data sample, except here we're gonna go up to -1. We're not gonna include it. So if you run it, it's great. And so now let's print it. Okay, we get means 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 1, 2, 3, 4, 5, 6. Okay. Okay, another thing we should do is normalize the data by subtracting the mean and dividing by the STD, which is the standard deviation. So we can say data normalized is equal to data minus data dot mean divided by torch dot square root of data. We didn't define the standard deviation yet, did we? Let's just do this. I mean, I guess we could say, instead of STD, we can say var. Alright. And, yeah, that's basically it. Okay, great, we've normalized our data, okay? Alrighty. So, I guess we've covered quite a bit here. We've talked about one hot encoding. We talked about the different colors and how it's great for categorical values. We talked about integer encoding and when we might use that, where fractional values aren't reasonable for the output. Okay, that's a place where you should use one hot encoding, and we did some implementation using the .scatter underscore, the in place method, to perform this one hot encoding. So you see the zeros here and the 1. And we normalize the data using some of the techniques we learned in our previous video. Okay. So there's one more thing, which we'll cover in our next video about tabular data, and that will wrap up our discussion with tabular data, and we're going to move on to time series next. But the next topic we are going to discuss that's related to tabular data is finding thresholds, and yeah, we'll talk more about that in our upcoming video. Okay? I hope you learned something new today about one hot encoding, because that was the main purpose for this video. And yeah, thank you so much, and don't forget to like, comment, and subscribe.